Yeah, sorry.
Oh, we go back out. Oh, never mind.
Rates of change. Okay, so have you guys heard of rates of change before?
Yeah.
Where have you heard that before? In terms of
Last year?
last year? Do you remember what it referred to? Okay. Well, let's see. Let's start with the basics. Have you guys ever heard of average speed?
Yeah.
Okay, so write this down. Did you know average speed is basically found by taking 2 points in time, how fast you're traveling at those 2 points in times, and then subtracting them, divided by the time that's elapsed? Average speed. Distance traveled divided by elapsed time. Come on, guys.
What is that little thing between the T's?
Between the T's, a comma? Yeah, 2 times. The interval is between time 1 and time 2. So for example, if we were going to travel from here to Billings, okay, we could say, I can find my average speed by figuring out at 1 hour how fast I was traveling. Let's say I was traveling 70 miles an hour, and then at hour 2, I was traveling at 80 miles an hour.
Oh, that's
What's my average speed?
75.
Absolutely. 75, right? Does this little piece right here look familiar to you?
No. Oh, it looks like that wire.
It looks like slope. Oh, look at you guys. This looks like slope because it is slope. Okay, see how it says f of t sub 2? That's like a fancy way of saying y, right? y2 minus y1. And instead of using an x, we're talking about time, so we're talking about the difference of time.
What's the bottom one?
T sub 2 minus t sub 1. Those are t's.
Everything's T?
For time.
Even on the top is T?
Yeah.
Oh, because F.
There you go. Look at that.
Sorry.
Okay, so average rate of change. This is one you're going to want to write down. You're going to want to highlight this because you'll see this a ton, and we'll come back to this. Okay, so average rate of change. Average rate of change. So I would write down average rate of change right here. And then I would write down those definitions there. Average rate of change is the change in y over the change in x. Sound familiar at all?
Yeah.
Like what? Oh yeah, slope. Interesting how that works. We're talking about slope. Average rate of change is slope. By the way, I'm going to call average rate of change, unless you want to write it all out, I'm totally fine with that. But I'm going to go average rate of change. That's how I'm going to refer to that.
Can you blow up the...
Blow it up? How do you feel about that?
Is that an H?
Yeah. On the third definition, it is an H.
Yeah, will you explain that?
Yep. See if I have GeoGebra on here. All right, does everybody have that written down? I'm going to go into a browser. No?
What is this serving?
17.
Oh, h does not equal 0. Can't divide by 0.
What's that? What's the right?
H cannot equal 0.
Warn me next time.
Good? So you guys have played with GeoGebra a bit, eh?
No.
No.
You. Just all freshman.
Never have.
Oh, so yes is the answer.
What was the question?
GeoGebra? Ever played with GeoGebra before?
No. I actually had.
GeoGebra. Let's see. Oh, there's a graphing calculator. Oh yeah, there we go. Okay, so let's talk about slope. Let's talk about average slope. Let's do something a little bit different than what you've worked with in the past. Let's talk about a basic function, x squared. Okay, so we're talking about the slope of x squared. Okay, so if I was going to, oh boy, I don't know how to do this. Oh, there we go. I want to put a point on here. Let's see. Can I put a point on there? Will that work? Oh, there we go. That's nice. And then I want to put, okay, yeah, so maybe, okay, so a parabola is slightly different than a linear function, okay, in the fact that it does not have a constant slope. Okay, it doesn't go up 2 over 1, up 2 over 1, up 2 over 1 forever. Okay, it changes as I move along the function. Okay, so if you were going to make an educated guess about the slope of the line at about point A, what would you guess? 1 over 1? So like basically if I was going to come up with a line that existed right through there, you see what I'm kind of looking at? That's actually called a tangent line. Okay, so let me see if I can draw a tangent line with this stuff. Construct bisector. I don't know if this will work or not, but no, that's not what I want. Wow, that's way away. Go away. All right, hold on. I'm going to pause this for a second. Let's do. Oh, that's because it's not working. Well, so basically, this is what you're going to need to do. I'm going to actually just do one of the problems off here. We're only going to do the first little section from this lesson. So I'm just going to steal problem number 1 from the assignment, and we'll just do it, and so you know how to do it. Okay, so all you're going to be doing is finding the average rate of change. It's called Snip. We're just going to find the average rate of change between these two given x values. Okay, so this piece right here is our x intervals. Okay, so this is our x1 and our x2. Okay, so the slope between x being 2 and the x being 3. Okay, so if I'm going to find the average rate of change, what formula am I going to use? The one that goes like y2 minus y1 over x2 minus x1, right? Just the slope. Okay, well, I have an x1 and I have an x2. How am I going to go about finding my y's? Plug them into the function. So what I have to do is start by taking my first value, so we'll say f of 2, and I plug it in so that I can find my corresponding y value. So would everybody agree that 8 plus 1 makes 9? Okay, so that, by the way, is my y2. Okay, and then I can plug 3 in, which is my x2. Oh no, sorry, I did that wrong, didn't I? My bad. That's my y1, because I did that first. Okay, and then I'm going to plug 3 into my function. So it's 3 cubed plus 1. So 27 plus 1 makes 28, and 28 is going to be my y2 value. Okay, so now all I'm going to do is take these values and plug them into my slope form. So what's my top going to be? Okay, so 28 minus 9 over 3 minus 2. So 28 minus 9 is 19, and 19 over 1 makes 19. Okay, so the slope between 0.229 and 328 has a slope of 19, so that's a very steep slope. Would you like me to do B as well? Does that make sense to you? One more time? Or do you got this? Let's do one more. I feel like you're kind of looking at me funny. Okay, so you see B now? So what's x1? Or excuse me, what's the negative 1? Whoops.
Negative 1.
Negative 1 is my x1, yep. Okay, and my 1 is going to be my x2. Okay, so I'm going to start by finding my corresponding y values. So if I plug in negative 1 into my function, my f of x, what do I get? Okay, so negative 1 plus 1 makes 0, good. And if I plug 1 in, I get 1 plus 1, which makes 2, good. So my average rate of change is going to be what goes on the top? 2 minus 0 over 1 minus negative 1. I'm going to say plus. So we get 2 over 2, which makes a slope of 1. Good there? Okay. You're just finding the corresponding y values and doing slope with it.
Why are those both x's?
Because it's an interval. It's giving you an interval between two x values.
Oh, they're not coordinates.
Correct.
Okay.
Those are x intervals. All right. So you ready for our limits?
I got a question.
Shoot.
So for number 1,
Mhm.
the answer, how would you write when you just write it out like 9 equals y1 and 28 equals y2?
Yeah. Yeah, and then you just say your average rate of change is y2 minus y1 over x2 minus x1, and
What? I didn't get that.
yeah.
Why is it called a tangent?
Why is it called a tangent? So a tangent, so there's secant versus tangent. So do you remember learning about circles? And a secant, do you remember what a secant line is? So a secant line is a line that intersects the circle twice. So you have 2 points and it would cross through the circle twice. So right now, average rate of change is kind of like the secant line of a function. Okay. The tangent is where you only have 1 point, so we're finding the slope at one particular point. Okay. That second definition, that one that had with the h in it, for the average rate of change, we are going to use that definition, but just not yet. So we're going to work with finding the tangent lines in a later section, because that'll be more calculus. We're going to use calculus to do that instead of doing algebra, because it's just why do an old method when there's a new method, right? Okay. So I'm going to show you guys how to find limits graphically and analytically, or maybe I will remind you how to do that. I'm going to just go down to examples and see if this looks familiar to you. I think last period did really well with it, so I think you guys will be fine. So I'm just going way down to the bottom here. We're going to take a look at question 1.
This is Ms. Smith. I have a copy.
Okay, so first of all, does this notation look new to anyone? Everybody has seen this notation before? Yes, okay. So this is asking us for the limit as x approaches 1 of our given function, which happens to be g of x, some super cool piecewise function. Okay, so tell me about how you find a limit.
It's like if the coming from both sides.
Good. Perfect. That's a perfect definition. So you have to you like trace the function from the left and from the right, and if they're going to the same place, then that's the point that the limit is. Okay, so you're looking for that y value from the left and from the right. Okay, so if I trace my function from the left and from the right, as we get really, really close to 1, okay, what would you say is the limit? So from the right, where is this function going to? 0. From the left, where is this function going to? 1. Are they going to the same place? No. So therefore the limit? Mike, you with me?
Yeah.
It's hard for me to answer questions for you when you're not paying attention when I'm teaching. Okay. What about as x approaches 2? Okay, so if we come in from the right, what is my y value approaching? 1. Coming in from the left? 1. So therefore the limit as x approaches 2 is 1. Okay. What about as x approaches 3? Okay. As we approach from the right hand side, what is the function approaching? 0. As we come in from the left side, what is the function approaching? So therefore the limit is?
What about that dot?
0. What about that dot? Okay, so that dot is the value of the function at 3. But the limit by definition is what is the function approaching as we get infinitely close to 3. Okay, so do you see the difference between those two things?
I just don't know the dot. Just chilling.
It's just a point. It's the function value at 3. It's just chilling. Sure, you can call it just chilling.
So like if there's no line in the top,
It's like the bottom one's open and the top one's like
So like if they asked us for the function value at 3, do you see the difference between this question and this question? This is what is the point?
1.
That would be 1, right? As opposed to the limit is what is the function approaching? Okay, what about D? What is the function approaching as x approaches 2.5? So we're looking at from the right and from the left. What would you say about that one? Probably about 1/2, 0.5. Both are equivalent. Pretty good there? One more?
Wait, I don't get that. Is that it?
Okay, so 2.5 is like right here, right? So if I trace the function on the right, as we get closer to 1.5, it's like right there. And from the left, it's like right there. So what's that corresponding y value? What's the height of that spot? I would say it's closer to 1/2. 2.5? Let's see if I can draw it. So do you agree that this halfway in between 2 and 3 is 2.5? Okay. So coming in this way, I'd be going to like right there. And going into this way, I'd be going to like right there, like halfway in between those two lines. This one is at 1, this one is at 0, like halfway between 1 and 0. So what's halfway between 1 and 0? Agreed.
How do you know what's from the left and from the right?
Oh, the difference between approaching from the left and from the right is if they have like a plus sign. So if you saw, let's say you saw the limit as x approaches, let's just say 0 from the right. Do you remember that symbol? Where there's a plus sign, or the minus sign is from the left. So we're not going to do right or left side of limits today, just straight up limits today from both sides.
Can we get our test back?
Sure, can I finish teaching? Oh.
Wait, so if it doesn't have anything you do from both?
What's that?
If it doesn't have like any sign, you just
Yeah. Yep. It has to come in from both.
Negative sign on the right side of the number, right? Not on
Yeah, right. Good point. Do you guys want to do one more? Or do we got this? You got this. Excellent. All right. Do you remember how to find limits algebraically?
Yes.
You know me too well.
It was hard for me today.
All right, hold on. Let's do limits algebraically. It's easier than that. You don't need a calculator to do this.
It looked like 0.75.
Whoa, that's huge.
Wait, so we're not doing it tomorrow?
Oh wait, no, you just plug it in.
Oh, yeah.
I remember now.
There you go. Okay, so finding limits algebraically, as long as my function is continuous, I can just plug it in. Okay, so do you remember what a continuous function looks like? Okay, so when I say continuous, do you know what I'm talking about? Continuous is a function that I can draw without ever lifting my pencil. It doesn't have any jumps or asymptotes in it. It's one single piece. Okay, so the only time you ever see not continuous functions would be like where you see vertical asymptotes, or sometimes there's piecewise functions that jump, or that's all I can think of off the top of my head right now. If I have x squared minus 13, what does that look like? Is that a continuous function? What does it look like? Parabola. Parabolas are continuous. I can draw them in one stroke. Okay, so all I have to do is plug and chug. Take that -3. You don't like that? What would you prefer?
Huh? Oh. I just makes you uncomfortable.
Plug and chug? Do you want me to do a dance? How about plug it in, plug it in?
Oh, no.
Oh, okay. What happens if you get this like one like this? Oh gosh, where am I going? Go away.
Can you show us when it's not continuous?
Yeah, let me do this one.
Why are you shady about me?
Okay. What about this one? Where would I start? If I plug this in, I would get 5 minus 5 over 5 squared minus 25. So on the top I get 0, and on the bottom I get 0. Now this is really important for us to realize what's happening here. If I get 0 over 0.
Don't you have to do 4.99999 and then 5.00001?
No, I think you're thinking one-sided limits maybe. Okay, if you get 0 over 0, that implies that there is a hole in the graph. Okay, there is a hole in this graph. Everybody with me? There's a hole.
Yeah, so don't just go on both sides of that hole.
No, it's easier than that. All I have to do is simplify the function. Okay, so if you look at this function, the top is linear, but the bottom is a quadratic piece. That quadratic piece can be factored. What is it factored to? X minus 5 and x plus 5, a perfect binomial. And what do you notice about the top and the bottom?
Cross out.
They cross out. So what's left over? 1 over x plus 5. Okay, so if I plug in 5 now, I get 5 plus 5 in the bottom. So this is going to go over 1 over 10. Do you want me to show you what this looks like? I feel like people who haven't seen this before needs to see this. Okay, so I want to graph my original function. And I'm going to use Desmos because GeoGebra is too hard for me to figure out. So I have, was it x plus 5 on bottom or top? X minus 5. What was it? X minus 5. And then I had x squared minus 25. Okay, so here's my function. And since I was going to 5, do you guys see that if I trace this function and I get really, really close to 5, let's see if I can hit it. Oh, there it is. Okay, GeoGebra, or not GeoGebra, what is this? Desmos will show you the whole, whatever this is. Okay, so you can see that I have no whole or no function there; it's undefined. Okay, now if I graph the new function that I just found, okay, the reduced form of this, is everybody following me? Come on, you guys, this is really exciting. X plus 5. So if I graph the reduce function, what does it look like?
The same thing.
It's identical, except for the one spot, right? They're identical except for the one single spot. So now that blue function here, let me get rid of the red one.
Get that out of here.
I can now see that we are crossing it exactly at 0.1, which is the limit that we got of 1/10, right? There are two identical functions except for at the whole.
Mr. Orley, can I get you to the office, please?
Super awesome?
Yeah.
Okay.
So why would you want to get rid of your role?
What's that? Say that one more time.
Why would you want to get rid of it?
Because the limit exists, because as x approaches 5 from the right and from the left, it still looks continuous on that red function that we had. So it's still going to that 1/10 spot. It just happens to be a hole in the graph. So the limit still exists. So that's why we use the reduced form.
You'll always be able to find the point still.
Yep, by reducing the function. Yep. All right, so your guys' assignment in the thing, yeah, it's in the thing. I'm changing this, so it's 2.1 to 2.2. On the 2.1 stuff, I only want you to go 2 through 6 evens. 2 through 6. Okay, and then for the second one, I want you to do. No, I want you to go 2 through 30. That's not bad. So let's do, instead of that, 2 through 30 evens on this page. Okay, and we'll talk about those square root things later.
2 through 6 evens or just 2 through 6?
I am going to come up with an extra credit thing, just not today.
Wait, is it 2 through 6 even? So you don't get extra credit 6.